Modulus of elasticity, or elastic modulus, is a key parameter when designing concrete structures. This value tells us how a material will behave under stress, giving us an idea of its stiffness. And it's actually a good indicator of the material's strength too. Now, to truly understand what modulus of elasticity is, we need to look at how it's derived. Modulus of elasticity, MOE, of a material is derived from one key concept, Hooke's law. As construction professionals, let's focus on the modulus of elasticity for materials like steel and concrete. I'll start by explaining the stress-strain curve of steel to introduce Hooke's law. Then, I'll move on to the stress-strain curve of concrete and how Young's modulus is derived. If you're not interested in the first part, you can skip to the next chapter, which begins at the 2:45-minute mark. Hooke's law is applied based on the stress-strain graph for the material. Take mild steel, for example. If you plot its stress-strain curve, you'll notice that up to a certain point, stress is directly proportional to strain. This is what Hooke's law tells us. For small deformations, stress and strain are proportional up to the proportional limit. In this region, if you remove the load, the material will return to its original shape. This is the only region where Hooke's law applies. The ratio, or slope, of the graph at this point, that is, stress to strain, gives us the modulus of elasticity. Now, just to refresh your memory, according to Hooke's law, stress, sigma, is directly proportional to strain, epsilon. We replace that proportionality with a constant, and that constant is the modulus of elasticity. This is a quick recap of your strength of materials knowledge. However, in this video, our main focus is to understand the modulus of elasticity for concrete. For steel, determining the modulus of elasticity is pretty straightforward. This is quite simple because steel is a ductile material. Hooke's law, which is all about elasticity, applies well to materials like steel due to its ductility. But when it comes to concrete, which is a brittle material, determining the modulus of elasticity becomes a bit more complicated. Since designing concrete structures requires us to consider the material properties of both concrete and steel, having a more accurate or better value for the modulus of elasticity of concrete is crucial. So, we use a different method to determine the modulus of elasticity for concrete. Let's take a closer look at why determining the modulus of elasticity for concrete is more complicated than for steel. As I mentioned earlier, concrete is a brittle material. When you examine the stress-strain curve for concrete, you'll notice that it's not only non-elastic in nature, but also non-linear. Because of this, the relationship between stress and strain in concrete is more complex, making it harder to define a single modulus of elasticity value like we can with steel. Because of this, when you unload concrete, it doesn't follow the same path back as mild steel does. After unloading, concrete doesn't return to its original state. It's left in a different condition than it was before. So, after unloading, the material gets strained by a certain amount, as shown on the graph. This means that we can't apply Hooke's law here, and we can't directly use the equation to determine the modulus of elasticity. Hence, we use various modulus terms and to get the slope of the stress-strain curve. We know that the modulus of elasticity, E, is equal to stress divided by strain. But when we consider strain of concrete, there are two types of strain experienced in concrete. 1. Short-term elastic strain. 2. Long-term elastic strain. Short-term elastic strain is caused due to instantaneous load applied on concrete, and long-term elastic strain is due to the effect of creep and shrinkage. Hence, we have short-term modulus of elasticity and effective modulus of elasticity, EC and ECE respectively. Let's first determine the short-term modulus of elasticity. Short-term MOI can be determined either by graphical method or by an empirical formula. Let's first check the graphical method. By graphical method, we can derive three modulus values for the respective concrete type. 1. Initial tangent modulus, ITM or EI. It is the slope of a tangent measured at the origin. 2. Tangent modulus, TM or ET. It is the slope of the tangent drawing to any point in the inelastic region. 3. Secant modulus, SM or ES. It is the slope of the line joining any point in the inelastic region to the origin. Initial tangent modulus is also known as short-term static modulus. The tangent and secant modulus gives the material behavior in the inelastic region of the concrete. Now, I am going to explain the features of these three modulus in detail. If you do not need the details, you can skip to the next chapter. So, from various observation, it has been seen that the initial tangent modulus is much higher than the tangent modulus, say by considering a point P on the curve. Secant modulus is applicable when the concrete specimen shows nonlinearity or when the initial tangent modulus do not provide much required information. As we discussed the graphical method of determining short-term elastic modulus, let's discuss the empirical formulas. As graphical method is time-consuming and difficult task, IS 456-2000 gives an empirical formula in clause 6.2.3.1. This empirical formula is given by EC is equal to 5000 square root of FCK. Let's say our concrete designed is 30 megapascal. Then FCK is 30 Newton per mm square. Hence, EC is 5000 square root of FCK, that is 5000 square root of 30. That is 5000 into 5.477. We get the modulus of elasticity EC as 27,395 megapascal. Now, as we have discussed the short-term modulus of elasticity of concrete, let us discuss the effective modulus of elasticity ECE-. The effective modulus of elasticity, as mentioned earlier, is influenced by the long-term effects of creep and shrinkage experienced by the concrete structure. It is given by the formula ECA is equal to EC divided by 1 plus theta, where ECI is the effective modulus of elasticity. EC is the short-term modulus of elasticity of concrete. Theta is the creep coefficient of the concrete structure, which depends on the duration or the age of the particular structure. This creep coefficient, theta, is specified in IS 456-2000, particularly in clause 6.2.5.1. If the concrete casted, as mentioned above, is currently 28 days of age and has a strength of 30 megapascals, we have already determined the value of short-term elasticity in the above example. Now, we need to calculate the effective modulus of elasticity by substituting the value of EC, which is 27.395 times 10 raised to 3 megapascals, into the formula. The value of the creep coefficient, theta, is taken from the table corresponding to the 28-day age of concrete, which is 1.6. By substituting these values, we get the effective modulus of elasticity value as 10.53 times 10 raised to 3 megapascals. So that's all about the different types of modulus of elasticity of concrete and how they are derived from the stress-strain curve. To get a complete understanding of how concrete behaves beyond the elastic range right up to failure, you should also learn about the idealized stress-strain curve used in design codes. We've already covered that in a separate video, and you can find the link in the description below or in the card above. If you found this video helpful, don't forget to like, share, and subscribe to the channel for more civil engineering technical concepts explained in simple terms for free. Thank you for watching, and we will see you in the next video.